Well, good evening, and thank you all for coming out. As you can see, that's me, so you're in the right place. I thank you for that very kind introduction. I'm really happy to be here. This is my first visit to New Zealand. I'm from Seattle, Washington, which is famous for its rainy weather, so I'm feeling right at home here today. So thank you very much. I'm going to get right into this so we have time for maybe some questions and discussion. I'm going to bring you something foreign and exotic, which is the American Concrete Building Code, ACI 318. The title of this talk is an overview of changes in the 2019 edition. And so you may immediately be thinking, but I don't know what was in the 2014 edition, so how am I going to know what the changes are? I'll try to bring you along as we go through, so don't worry about that. And then we have a new edition of the code coming out in 2025. In the unlikely event that everything goes as planned, it'll come out in January or February of 2025. So with that, let me get started. Two main parts to this presentation. The first is I'll be talking about the ACI 318 code, how it's organized, and some of the things that have been newly introduced in terms of concepts and changes in design provisions. And then I'll finish up with a brief overview of things that we're currently working on for the 2025 edition. So hopefully this will give you a flavor for the direction of concrete research and code development in the U.S. Of course, there's a lot more background that I could fill in about the basis of the code as a whole, but hopefully this will get you interested and maybe provide you with some information on where we're headed in the U.S. with our concrete codes. Just a warning, if you are familiar with the 2014 edition, this presentation is not a complete introduction to all of the changes in the 2019 edition. I have to sort of put that disclaimer there. So with regard to the code in general, it is organized currently since 2014 into 10 parts as shown here. I won't go through all of them, but you'll be particularly interested perhaps in the seismic part down here in the lower left. And I will be talking about some key changes and trends in most of these sections as we go through. All right, first, existing structures. Very often we have to evaluate existing structures for their strength, their capacity, and sometimes for seismic capabilities or seismic resistance. This code is for new design, but there is a provision that says if you want to use this code to design elements as part of a retrofit, it's perfectly valid and is permitted. The commentary to that statement points the reader to another document. It's actually another building code called ACI 562, which is a official code for evaluation and repair of existing buildings. I just want to caution that is not seismic evaluation and upgrading of existing buildings. It's all things non-seismic, although it does point to some other places for seismic. So this is how we deal with existing buildings. But I want to also point out there's a chapter 27. It's I believe it's the very last chapter of the code. This chapter is titled Strength Evaluation of Existing Structures, and you might think, aha, that's what I need to know if I have an existing structure and there's a change of occupancy and I need to design, say, or check for higher loads in the building. It's really what it applies to is new construction where there's some doubt about the strength. Perhaps concrete test strengths came in low, or there was an error in construction, or for some other reason, the building is new but needs to be evaluated. So we as engineers understand very well how to approach an existing structure that may have deficiencies and analytically evaluate its strength, taking into account those deficiencies. There's another approach, which is load testing. This isn't used very often in the U.S., but when it is used, it's a very helpful and definitive proof of the capacity of a building. There are two procedures available for testing the strength of a new building. And let's just imagine that we're testing a two-way concrete floor slab. The first method is the monotonic procedure, which is described in ACI 318. This, you probably can't read the fine print, but up here it says you load this up in steps over quite a long time, and you then hold that load for 24 hours, you release the load, and wait another 24 hours and measure the residual deflection. That is a procedure that takes at least 2 days and probably more like 3 per test location. So it's a very slow procedure. There is another method, a cyclic procedure, which is in a different ACI document, ACI 437.2. And the scale here is on the order of 2 hours. It's a cyclic load, unload, load, unload, higher amplitude load, unload, and so on. This, of course, then is a much faster and more efficient way to test the capacity of a new structure. So just letting you know about those two approaches. Let's get into specific types of concrete members. For one-way bending, one-way slabs, the ACI Code has something called structural integrity reinforcement requirements. These are very minimal reinforcement that is required to be continuous through an element, whether it's a beam or a slab, that is developed at each end. It's just a minimal sort of notional amount of reinforcement to help forestall progressive collapse or disproportionate collapse. It does not take the place of a progressive collapse analysis. It's just a minimum amount of reinforcement to help stop a sequential collapse. And there are new provisions now for this integrity reinforcement for one-way slabs, and it's very similar to the requirements for beams. I won't go into the details, but it's a very simple check and a zero or low cost detail, because the bars are probably that you need are probably already in the design. Moving on to two-way slabs, we had since I think time began, we had two methods in the code that were meant to be approximate methods. These were introduced pre-computer-based analysis days. One is called the direct design method, and the other is the equivalent frame method. And these are for two-way slab systems that may, well, it's a two-dimensional sort of approximate prescriptive method. We have found that those are very rarely used any longer. But they're still valid. There's nothing wrong with them. They're just approximate and conservative. So we removed them from the code, but we put a statement in the code that those methods are still valid to be used, either the direct design method or the equivalent frame method. You just have to look back to an earlier version of the code, but you can still use them. We just are saving some trees by not printing as many provisions. Here's an interesting one that has to do with openings near columns in two-way concrete slabs. Previously, up until 2019, the rule was that if there was an opening, you can see some illustrations of openings near columns or near slab edges on the right, that if an opening was within 10 times the overall thickness of the slab, H is the total slab thickness, then one needed to reduce the effective perimeter for punching shear. And in essence, those openings would have an effect on the punching shear strength. That number has been increased was 4H and is now 10H. Was 10H and is now 4H. So these openings can exist a fairly nominal distance from the face of column and not affect you don't have to check necessarily, you can, for if you like, but you aren't required to check for the effect of those openings. Kind of an interesting liberalization of the code. Another new provision related to two-way slabs is that in the United States we have some, it's actually quite a common form of construction is to have 2 stories of concrete structure starting at the ground level, and then above that have 5 or 6 stories of light wood frame construction. So that concrete portion is called the podium, and all of the wood shear walls in this 5-story wood building on top of the podium bear on this podium slab. It's been discovered that if the podium slab is very thick, and in this case I'm showing a slab thickness of 2 feet, which is about 60 centimeter thick slab or greater, the punching shear crack may extend past the end of the top bars, as you can see here. That's because it has enough distance and enough thickness to propagate out past the ends of those bars. So we have increased the length of those top bars for very thick slabs, as shown in this slide. On the top is the provision for a normal or thinnish slab, let's say 30 centimeter thick slab. Once the slabs get quite thick, there's a secondary check now to extend the bars further, as shown down here, so that they extend past the path of propagation of that punching shear failure surface through the top of the slab, and the bars are crossing that crack. So it's just we recognized a condition where something was not quite right, and we fixed it. Okay, post-tensioning construction. In some parts of the United States, it's very common. For instance, in the area where I live, the Pacific Northwest. In other areas, it's very uncommon. So the post-tensioning, the use of post-tensioning varies quite a lot across the United States. One thing that we updated just to simplify things was to make, when you have a post-tension slab, you also are required to provide some non-post-tensioned deformed reinforcement. We simply changed the spacing requirements for the maximum spacing of that non-post-tension reinforcement so that it matches that for non-post-tension slabs. So it's the same for both types of slabs. That maximum spacing is either 3 times the total thickness of the slab or 18 inches, which is about 450 millimeters. Also related to PT is some forms of PT construction for slabs in particular have groups of tendons that are very close to each other. We call these banded tendons. There may be as many as 8 or 10 tendons very close to one another, and then the anchorage for the post-tensioning, the forces are very close together in a line along the edge of the slab. To prevent bursting of the slab under those very high localized pressures, we require what are called backup bars that are shown down here, and hairpin bars, which also help resist the high tensile bursting stresses that occur in this zone just behind the anchor. So that's a new provision related to that kind of reinforcement, or that configuration of reinforcement. Moving on now to a new type of member, walls. We've had a change in philosophy related to cantilever retaining walls, in that we are now treating them as not walls. They aren't included in the chapter 11, which is about walls. They're included in the chapter about foundations, chapter 13. We reasoned that retaining walls, cantilever retaining walls, are really foundation elements, closer to foundation elements, as opposed to freestanding concrete walls. Part of the reason is that the lateral loads on the stem of the wall are the dominant load that controls design. So these are now treated as foundation elements. Another kind of detail, but I think one important that helps clarify the placement of reinforcement is prior to 2019, we had some kind of obscure, actually difficult to understand provisions about the number of layers required of vertical reinforcement, vertical and horizontal reinforcement in a wall. If the wall was greater than 10 inches or about 250 millimeters thick, you needed, and you still need, 2 layers of reinforcement, 1 near each face. We had some rather confusing rules about half needs to go here, 2/3 over here, and we got rid of all that. We just said you need to put 2 layers of bars in, and typically designers are going to put half in one face and half in the other face. We do have an exception for single-story basement walls, which are used a lot in single-story basements for commercial and residential construction. This requirement is less important. So simplification and clarification there. Now, foundations is, of course, major use of reinforced concrete, and we are constantly updating those provisions in the 318 code. We added design provisions for, again, cantilever retaining walls are in chapter 13. We've also been doing a lot of work with provisions related to deep foundation design, where deep foundations are driven piles, cast piles, auger cast piles, various deep foundation elements that are used particularly in poor soil conditions. We have also added some other provisions related to minimum concrete strength for foundations, for both shallow and deep foundations, and cover, meaning the concrete cover over reinforcement to control corrosion. I mentioned earlier that we moved cantilever retaining walls into this chapter on foundations. We also changed the basic approach to design of cantilever retaining walls. Previously, they were treated as a wall, and they were subject to the wall design provisions. Most walls are not governed by very high face loads or lateral loads on the wall. Those are what I would call walls. Retaining walls are heavily loaded out of plane, and we decided to treat those as slabs, so cantilever slabs. So these stems are now designed as a cantilever slab, a one-way cantilever slab, which I think makes a lot of sense. And here shows the difference between the last edition of the code and the current, just illustrating that on the left you see a little bit more complicated requirements for the total minimum reinforcement in a wall versus the minimum reinforcement in a one-way cantilever slab. And so we've migrated over to a simpler and I think more rational design process for cantilever retaining walls. Here's a big important change. in the US, for reasons that I don't understand, we've had deep foundation provisions for concrete type deep foundations in 3 different design codes. ASCE 7, which is a loads code, not a concrete design code. The International Building Code, which is the master code for the US that refers to material codes like the ACI Code, there's a wood code, masonry code, and so on. But there were provisions for deep concrete foundations in the International Building Code, which they shouldn't be there. All of them should be in the ACI Code. So we are gradually in the process of trying to bring all of those provisions into ACI 318. In 2019, we were successful at bringing many of them out of those other codes into ACI 318, and we hope to complete that process in 318.25. We'll see. Anchorage to concrete, everyone's favorite subject. We actually reorganized this chapter so that it mimicked more closely the the organization of the other member type chapters. And we also added post-installed screw anchors, the type you see on the left. I think those are very useful in some situations. And also attachment with shear lugs, where shear lugs are these projections on the bottom of a steel plate that are intended to provide additional shear capacity at the base of a steel column or other attached steel element. However, there have never been any provisions describing the capacity of those shear lugs and the failure surface in shear for this lug projecting into the concrete. So those are in the code now. Also, I should just point out while I'm thinking about it, I'm going to give a PDF of all these slides to Rick, and they'll be available for you. So if you miss something and want to refer to it later, you can get a copy of these. So now let's talk about seismic. Really important subject, both in the US and New Zealand. I want to point out there were quite a few changes to the seismic provisions between 2014 and the current 2019 edition. And I wrote 2 articles in the magazine Concrete International with S.K. Ghosh on summarizing every change in great detail, except for the deep foundation ones, because that would be like a whole nother 2 articles. If you look online at Concrete International, I believe you can just find those for free. And if you want to know what the current seismic provisions are in the 2019 ACI Code, that would be a good place to get a very condensed tour through those. So, another big change in seismic was we added what we call higher strength reinforcement grades to the code for seismic force resisting systems. This table here, which is very small, but I've just highlighted with green boxes the updates that are included to allow higher strength reinforcement. And what do I mean by higher strength reinforcement? We've introduced the possibility of using 550 and 690 megapascal strengths for certain elements of certain seismic systems. You have to read through this table in great detail. If you get a copy of these slides, you can see those. But this table 20.2.2.4a is very useful because it covers all applications of reinforced concrete and what grades of steel reinforcement are permitted for each of those applications. So it is a complicated table, but it is a complete picture of reinforcement grades that are permitted under the ACI Code. All right, now let's talk about special seismic systems. We have what we call, whoops, let me back up a little bit. We have what are called special moment frames and special shear walls. Special means they are detailed for the best possible seismic performance. There are also intermediate systems and ordinary systems of various or defined standards for different types of lateral force resisting systems, which are deemed ordinary, intermediate, and special. I'll just describe the special ones here. This is where these higher grades of reinforcement are anticipated to be used. The only changes really relate to the spacing of shear reinforcement or confining reinforcement for the higher grades, because presumably you are either using the same size or a smaller size bar. You're allowing a higher stress because they're a higher grade longitudinally. Therefore, their tendency to buckle laterally is higher than for the lower grades. So the lateral support of those bars needs to be closer together. Therefore, the hoop or tie spacing for the higher grades is reduced compared to the lower grades. So we just see that here. Whatever's in green here is a new, slightly closer spacing for one of the higher grades for 550 megapascal in special moment frame beams. I won't go through these in detail, but also the spacing in, let's see, stirrups in special moment beams has a slightly different requirement for 550 megapascal bars. I don't know why I keep double clicking here. Columns in intermediate moment frames, a change in spacing over these plastic hinge regions for the higher grade reinforcement. Columns in special moment frames, more reduction in spacing for the higher grades of reinforcement. Okay, so and now special structural walls. Again, one of the things that we allow now in special structural walls is higher strength or grades of reinforcement. These are 6 of the major changes related to special structural walls or shear walls for resisting seismic loads. And I will go through each of these very briefly, but they are the cutoff or termination of longitudinal bars in special boundary elements. Special boundary elements are illustrated here. They're the highly reinforced and confined regions at the edges of walls. We have an update in the required minimum reinforcement ratio at the ends of walls. Shear demand for certain walls has increased very significantly. We have a drift capacity check, which is essentially a minimum wall thickness check in disguise. And then we have new provisions for detailing and special boundary elements, which are starting to look a lot like the provisions that you use here. And then we have a new old structural system, ductile coupled walls. I'll explain a little bit more about that when we get to it. So these longitudinal bars running up the, the main flexural reinforcement in the ends of walls, we used to require that they be continued past the point at which they were no longer needed by 80% of the length of the wall. So if you had a very long wall, you could be required to extend past the point where you didn't need those bars anymore, the vertical longitudinal bars, a quite long distance, 2 or even 3 stories, which doesn't really make any sense. It turns out that 0.8 provision came from a kind of crude beam analogy for walls that is not actually correct. So we've changed that to at least 12 feet, or what is that? That's about not quite 4 meters, at least 12 feet, but not more than 1 bar development length above the next floor. So gone are the days when these bars have to be sticking up in the air 2 or 3 stories. At most, they need to be sticking up beyond the next story 1 bar tension development length. So that has improved constructability quite a lot. We have some new restrictions on the use of lap splices in very particular zones. These zones are the boundary regions shown in orange here. Here's a plan of a T-shaped wall, and here's an elevation. These regions that are shaded in orange are where lap splices are excluded only in these orange regions. Between the orange regions, above and below the orange regions, lap splices are permitted. This is for special concrete shear walls. These, I could go into the reasons for this, but it takes a bit to explain. However, the alternative here would be either to not do any splicing in that region or use mechanically coupled bars. Contractors don't like that because they're expensive. They do reduce congestion, though, reinforcement congestion, so that's an advantage. But this is new. It's causing a little consternation amongst contractors, especially, but we think it's a good an improvement. All right. Now comes a provision which was adopted in 2019 and was originated by Rick Henry and Ken Elwood, and who have both contributed to the ACI 318 Seismic Committee, and we appreciate their contributions. So based on failures observed in Chile and New Zealand, if a wall does not have enough area of reinforcement near its ends, what happens is when the wall cracks in tension, only a few cracks, one or maybe two cracks develop, which is not a good thing because that concentrates all of the strain, the plastic or the yielded strain, in just one or two locations, and you don't get the benefit of spreading out spreading out that inelastic action through a number of cracks. And these are examples actually that are up here, I believe, in the code, these illustrations. But if we provide a minimum, shown here by rho is 6 square root F prime C over Fy. Those are inch-pound units, so be careful. Look at the metric version of the code to find the correct version for New Zealand. We end up with many well-distributed cracks, which is really the ideal way to utilize yielding of reinforcement to dissipate energy in a structure as it undergoes inelastic earthquake displacement. And so that is a new requirement. We have found that actually it doesn't govern very often with the way, at least in high seismic regions, walls are designed in the US, but occasionally it does. So it's a good thing that it's in there. Here's maybe the biggest change in the US code for 2019. It is the so-called amplification of shear. This is the design shear forces for walls. It affects mainly walls that are tall and narrow. It's a phenomenon we have known about for a long time, and by we, I mean both researchers in New Zealand and in the US, but it has never found its way into the code. The phenomenon that we're referring to here is an increase in the shear demand on reinforced concrete walls due to two factors. One is overstrength of the materials, so overstrength of the flexural reinforcement above what we assume in design. So maybe you have a 20% overage in yield strength, but you designed for the specified yield strength. That additional moment capacity leads to higher shear. So there's a factor greater than one related to the shear demand on a wall that is caused by overstrength of materials, both concrete and steel. The second factor is higher mode effects This is, we typically visualize concrete shear walls, especially in tall buildings, as being swaying elements. We may occasionally think about a second vibration mode. But what we don't usually think about, at least in our kind of general understanding of the behavior of tall walls, is the contributions of higher modes, third, fourth, fifth, sixth, seventh. Those add up to a fairly significant increase in the shear demand, those higher mode effects on the shear walls. So these two factors are taken into account in terms of big omega sub v and little omega sub v. They are multipliers on the shear v sub u that you would get out of your normal analysis. I should point out, if you do a nonlinear response history or nonlinear time history analysis of a tall building, say a concrete core wall system, you have effectively satisfied this already. This is to account for situations where a designer is not doing that sort of analysis that would bring up these effects as part of the analysis. But we want to make sure that these increases are included in all designs. So we have these two factors. What are their values? They're shown here in this table. They big omega sub v typically has a value of somewhere between 1 and 1.5. It could be a little higher. It depends on the aspect ratio of the wall, the height versus the length, or the width, height versus the length of the wall. There's some conditions on that. And then little omega sub v, the higher mode amplification, is a function of the number of stories in the structure, as shown here, and the aspect ratio of the wall, as shown on the left. I will point out that this n sub s value is calculated based on a building height in inches. So please use the correct formula if you're doing it for metric units. I mentioned that there's an effectively a minimum wall thickness requirement that has been introduced. That is in this section, 1810.6.2. You can do it the simple way or the hard way. The hard way is option 3, which is difficult to use because it requires an iterative solution, which can be quite cumbersome. You can take the shortcut approach, which is direct in that the thickness of the wall, B, has to be greater than 0.025 times the length of the wall times the distance from the, or the depth of the neutral axis in the wall, the distance from the compression face. So that's there. We find actually in US practice this very rarely governs, but occasionally it does govern. And it's important to have a minimum thickness of wall to forestall lateral buckling of a wall that's too thin. If you have a very slender wall, when it's loaded, its edge is loaded to compression, it can buckle laterally. Now we have new and improved detailing provisions for the confining zones at the ends of walls called the special boundary elements. And these are starting to look back up. These are starting to look a lot like what you use here. We have now requirements for overlapping closed hoops within these boundary regions at the ends of walls. We also have requirements for 135-degree hooks at each end of cross ties, and a requirement that every every pair of bars within the boundary zone have a cross tie, including through the length this way. In addition, we have a requirement that 135-degree bends are required on all bars, cross ties outside the special boundary zone, which is shown by this The special boundary element is given by this length L sub BE. So this is a big change. We previously could use cross ties with 90-degree hook on one end, 135 on the other. Contractors like these because you can stick them through, hook them, and jam them home, and they're easy to install. This is much more challenging, so we're dealing with a lot of grumbling about that. Okay, and I already pointed out this slide relates to these cross ties in what we call the field of the wall outside the special boundary element region. We have introduced a new type of wall, which is an old type of wall, and we've given it a name, ductile coupled walls. There are, I believe, millions of these walls constructed around the world. You can see they're very familiar. It's a solid wall and another solid wall with connecting beams. Those beams couple the two walls and make them act together. In the extreme, they would act as one single wide wall. If those coupling beams are very weak or flexible, the behavior would approach that of two independent walls. However, this type of wall has never been explicitly defined in ACI 318, and that is important because until that definition exists, the other code that is dominant in the U.S. For loads and loads and structural system definitions, ASCE 7 will not specify seismic parameters related to designing this kind of wall. Somehow we have gotten away or gotten around having those parameters for decades. Finally, we define this ductile coupled wall. The definition is given here. I won't go into it. It has to do with some geometric constraints on these elements. And if you meet those requirements, you have a ductile coupled wall, and then you have seismic design coefficients or parameters in ASCE 7 specifically for ductile coupled walls, which are actually more generous than the values we had before we defined ductile coupled walls. So that's the reasoning for doing this. Okay, so I have talked about some general trends with the 2019 code. I want to just very briefly go through some things that we're working on for 2025, just for your interest. We are writing a new appendix for the code. So the code historically has had various appendices on different topics. Once an appendix goes in, very often it moves in to become its own chapter in the code in the next edition. In any case, we have written an Appendix N, which is for sustainability provisions. This is not a chapter which specifies limits on global warming potential or other metrics for defining the sustainability of a concrete mixture or a concrete product. It simply says if you are going to define the global warming potential or the life cycle carbon load of a building, this is how you ought to do it. But we don't say what the limits are that you might have to meet. We believe those are better determined by local governments, local jurisdictions, because they're highly location dependent, what's achievable and what's not achievable in terms of global warming potential for individual mixtures. This is an outline. There's 4 parts. They're very basic. They don't get into a lot of detail, but they do establish the proper way to quantify sustainability for concrete structures. We have an Appendix A, which appeared in 318.19. It's being updated for 318.25. This describes the basic outline of the acceptable ways to use nonlinear response history analysis for design of concrete structures, for seismic design in particular. We had to write this because another code started to write provisions for doing nonlinear response history analysis of concrete structures, and we wrote them a letter and said, no, you shouldn't do that, and we'll take care of it. So we did it. That is evolving. It will probably get more complete with each edition of the code. Anchoring to concrete, we aren't changing too much, but we are exploring this question of if you have a reinforcing bar of a certain length and an equivalent anchor of a certain length, a adhesive anchor or a wedge anchor or whatever, why is there a difference in the way we treat the development of those two things? And the other thing is, if you have a group of embedded bars and you have a group of closely spaced concrete anchors, why is there a difference in the capacity of that group, at least under the ACI 318 rules? And maybe there should be. This subcommittee, Subcommittee R, is exploring that, and we'll have some a few but important updates to the code regarding groups of bars and their development intention. We have a new appendix under development related to performance-based wind design. You're probably familiar with performance-based seismic design. In the US, there's emerging now a trend to do wind design, especially for tall buildings, using a performance-based approach. And so again, in response to other codes developing provisions on that kind of design, we're developing an appendix for performance-based wind design in ACI 318. We have found that the new provisions introduced in 318.19 for one-way shear strength have some issues. Frankly, they don't work very well for tall cantilever retaining walls and for some types of very thick footings, as illustrated here. We're updating those to try to take care of that problem. It is definitely a problem, though, that we are fixing. Briefly related to precast and post-tension concrete, we used to treat those in one subcommittee. Now we're treating them in two subcommittees in ACI. In addition, ACI has authorized and initiated the development of two new separate concrete codes, one on precast structural concrete, 319, and the other on post-tension structural concrete, ACI 320. Those are under development. I really don't know if they're going to finish them by 2025, but they are completely separate from ACI 318. Even though 318 contains provisions for precast and post-tension concrete design, these codes will go further into more details and so on. So the basics will still be in 318, but there will be these specialty codes that will provide more detailed guidance for more complicated situations. So that's it. I talked about some changes and trends in the evolution between 2014 and 2019, the additions of ACI 318. And I just gave you a highlight of provisions that are being considered for 318-2025. I just wanted to point out, this is not an advertisement, it's just some advice. If you're interested in ACI 318 and its use, there is a product that ACI has called ACI 318 Plus, which is an electronic version of the code. It allows searching by keywords. It allows clickable links to research documents and so on. This is some audio that is associated with this slide somehow, and I've got to get rid of it. Okay, thank you very much. I don't know how we're doing on time, but I'm happy to stay around for any questions or discussion. Thank you.